Okay, good afternoon. Here we are at the first video of the semester, and I had to do a sound test before and it didn't work, so now hopefully it's working. And here we are. Let me get my colors together here. Okay, so let's recall. Yesterday we did a lot of definitions, and one of the major definition was what a first order linear ODE is, or what linear ODE is, and this is our first major topic, first order linear ODEs, and in general first order ODEs. So okay, so in this recollection we're going to look at a standard form here, and using the notation we have a t function times y prime plus another t function times y, and this equals some t only function. And it's important to note that this a1 function is non-zero on some interval I. It's usually all the real numbers, but if there are t's involved, sometimes there can be a point you have to take out or a whole section. Okay, but this is not useful for solving, because that's our goal here, is how to solve these. Not useful, it's not useless. What I said was it's not useful for our purposes. So step one is we're going to divide through the entire equation by this a1 function, the one in front of the y prime. And since it's non-zero, that division is legal, and what you wind up with is you have y prime plus the a0 function over the a1 function, that guy times y, and that equals the b function over the a1 function. Okay, now it's important to note that this is just a new function of t, as is this. So we're going to rewrite these as p of t, and this guy as g of t. Okay, so now our standard useful form is this. It's y prime plus piece of t y equals g of t. And for the theory I'm about to present, we're going to drop the arguments. It's just less writing and it's cleaner, and so we have y prime plus py equals g. And just remember that, you know, p is actually a function of t only, and g is actually a function of t only. All right, so step one here in solving is to get the equation into this form. And at the end of this little development, we'll lay it all out really clear. So this will be step one in our solving algorithm. Okay. Now this technique comes from Leibniz, who's one of the famous grandfathers of calculus. And so what we're going to do is consider the left-hand side of this equation here. So we're going to look at this only, right? Make it really big here. Y prime plus py. This is how Leibniz thought, not me. This looks sort of like the product rule from Calc 1. Right, so pretend you had like a 1, or let's say you had a p prime here, right? This would be the derivative of py prime using the sorry, didn't mean to write that. I meant to put a 1 here. So it's something y prime plus something y, which looks kind of like the derivative of a product, but not quite. So here's what Leibniz did after much thought. So here's what we're going to do. We're going to multiply through equation 1 up here, right? So this guy, this 1, by an undetermined function mu of t. So it's a Greek mu instead of u. Okay. And we don't know what this is. It might not even exist, but it will. And so when you do that, you get this. You get mu y prime plus mu py equals mu g. All right, here's where the magic happens. I'm going to go back to white here. If, this is a big if the left-hand side of this equation had the form mu y prime plus u prime y for some mu, then the left-hand side would be the derivative of uy, right? Which equals this thing I just wrote down, uy prime plus u prime y, okay? So that's a big if, right? If that was the case, then a lot of good things would happen. So the good thing would be, so if we took this star equation, and by magic the left-hand side was uy prime, we would have that's equal to the function mu g. And if you integrate, well, here's even better. This is even better. By the FTC, the left-hand side becomes mu y, and the right-hand side becomes the integral of mu g dt. And then you divide by mu, you get 1 over mu, integral of mu g dt, and we've solved the ODE. Okay, assuming this integral exists. But I mean, that was just a pipe dream that Leibniz had. He said, you know, if all this was true, which was supposed to be highlighted, but I guess I need to find a different highlight color here. Let me see. No, it's not going to work now because I've already highlighted it. So the question is, if we could find some mu that made that equal to this, everything would work. Okay. So this leads to the next question, or actually the big question. Is there some mu such that, make sure I get it right here. Mu, okay, so it's mu y prime. Mu y prime plus mu py equals mu y prime plus mu prime y, okay? So is there some, that has an e, is there some function mu such that this equation is true? Okay, well, let's solve for mu, see if it is. Straight away, these guys drop out. All right, that's looking good. Mu prime y equals mu prime y. Okay. It's clear that y is non-zero for some interval, probably all the real numbers. So you can divide through by that. So the y's drop out. So now we have mu p equals, and I'm going to rewrite mu prime. Mu prime is d mu dt. Okay. And do some dividing here. You get p dt equals 1 over mu d mu. And remember, p is a function of t only. All right, well, everything on the left is in terms of t and everything on the right is in terms of mu, so integrate both sides. This equation. So we have the integral of p dt equals the integral of 1 over mu d mu. And let's keep in mind what we're doing here. We're trying to solve for mu. Okay. So over here in our brain bubble, remember we're trying to get a solution for mu. Okay. All right, well, the left-hand side integrates nicely. This becomes the ln of the absolute value of mu plus some constant k. And that's equal to this integral. So, okay, now we use calc trick 134. This is the e to the ln trick, right? So if I raise the left-hand side to this thing, which hopefully will be a number, and I raise the right-hand side to this old thing, do some algebra on the right-hand side. We have e to the k times e to the ln of u. And e to the ln of anything is the anything, so I have e to the k times the absolute value of u. And I'm going to let e to the k equal 1. So this becomes the absolute value of mu. And sure enough, we solve for mu. And since e to any power is always positive, this goes back to this. So mu is equal to e to the integral of p dt. And this is what we were looking for. Right? So, believe it or not, if you unravel all of this, just keep going backwards and backwards and backwards and backwards, we were looking at this question. Is there some u such that that equals that? And the answer is yes. It's mu equals e to the integral of p dt. So computing that becomes the second step in our algorithm, right? So as we build our little algorithm for solving first order ODEs, step 1 is to get it into this form. And step 2 is to compute mu sub t, which is e raised to the integral of p dt. And this gives us what's called an integrating factor. Okay. And now 3, following what we did above, multiply through 1 by mu. And by construction, what you get is you get mu y prime on the left-hand side equals the integral of mu g dt. No, I jumped ahead there, sorry. Let me back this up. Okay. Then by the FTC, oops. Then by the FTC, we have mu y equals the integral of mu g dt. And solving for y, we have 1 over mu integral of mu g dt. And that's our solution. Okay. Right, so the whole thing really boils down to A, putting it into the right standard form, B, computing this mu where a lot of trouble can be found, and then 3, doing this grunt work, integrating and using the FTC. All right, let's do some examples here. Solve the ODE y prime minus 2y equals e to the 2t. And note it's already in standard form. Okay, and just so I'm crystal clear here, p sub t equals -2 and g sub t equals e to the 2t, right? And that's standard form from part 1. Okay. So it's already in standard form, so 2. So mu sub t equals e raised to the integral of p dt, which is e to the integral of -2 dt, which is e to the -2. That's our mu. Should be red. Okay. Step 3. You multiply through by mu, so you get e to the -2t y prime minus 2e to the -2t y equals e to the -2t times e to the 2t. Okay. All right, so here's mu. Here's mu. Here's mu. So I multiplied through the whole equation by mu. And let's do a simplification here. That's nice. All right, and here's where the magic happens. The left-hand side by construction becomes what? The derivative of e to the -2t. Now, if you don't believe me, apply the power rule to this. Right? You get e to the -2t y prime, then you have y times the derivative of e to the -2t, which is that. Okay. All right, now use the FTC, and we have y e to the -2t equals the integral of 1 dt, which when you integrate becomes t plus a constant. And lastly, solve for y. So you have y equals t e to the 2t plus c e to the 2t. Okay. And this is the general solution. Oops. Okay, now let's say we wanted to make this into an IVP. And we set some initial conditions. Let's say the initial conditions we gave with this problem were y of 0 equals 2. So when you plug in 0, you get 0 e to the 0 plus c e to the 0 equals 2. That says c equals 2. And so the particular solution becomes t e to the 2t plus 2e to the 2t. And this is the particular solution. And just a note here, this is where you can end if you were turning anything in for me. Your book likes to simplify things even further. It's not a big deal to me, but they would write this as, that's how the book would write it, just so you think you've got it right. They always do this kind of simplification. Okay, so I have a bunch more of these to do in class with you all, and when you're ready, let's chat.